Hello, can you hear me? Okay, yeah. Let's start the recording now. So, welcome to week seven's problem solving session. Today we'll first solve last year's week seven assignment and then this year's week seven practice assignment. And if we still have some time, we'll look at this year's week six assignment. Okay, so let's start. The first problem is suppose a language L has a circuit of poly n size and depth log n square whole cube. If all the gates have unbounded fan-in, then L is in which of the following classes and select all the correct answers. The options are NC2, AC3, NC3, AC2, NC4, and AC4. So which of these are correct? B is certainly correct. That's in AC3. Are any other options correct? Well, AC3 is contained in NC4. Yes. So AC3 is certainly contained in AC4. And AC3 is also contained in NC4, right? So B, T, E, E, and F are correct. So yeah, let me just write this down one. So the depth is equal to log n square cube, right? Now log n squared is just 2 log n. So the depth is order log cube n. Since gates have unbounded channel, this means that hmm, L is in AC3. However, for all I in N, ACI is contained in NCI plus 1 is contained in ACI plus 1, right? So L is also in NC4 and AC4. Is this fine? Yeah. And have you seen this in class? That in particular ACI is contained in NCI plus 1? Okay, yeah. So I suppose you have seen this in class, so I don't need to prove this. Okay. Then let's look at the next problem. The next problem is which of the following languages we know for sure is or are in P slash poly and select all the correct answers. The options are 2SAT, clique, which is defined as tuples of the form G, comma K, where G is a graph and has a clique of size K. 3SAT and parity. So which of these are for sure in P slash poly? Yeah, A and D are here. And what about B and C? So, okay, yeah, let me just write it down and we can talk about B and C later. So yeah, 2SAT and parity are both in P and P is contained in P slash poly. So A and T are correct. Now, clique and 3 sat are NP complete. So if either of them NP slash poly, then pH equals pH collapses, right? And yeah, so right now the question of whether pH collapses or not is an open problem. So we cannot say that we don't know whether B or C are in P slash poly or are not in P slash poly. So we can't say anything about B and C. Is this fine? Yeah. Okay, so then let's look at the next problem. The next problem is, suppose we are able to show that NP is contained in P slash poly, then which of the following statements is true? This is related to the previous problem and it's just a recall question. The options are P equals NP, P not equals NP, pH equals sigma 2, P and pH equals NP. So which of these are correct? Yeah, it's C. pH collapses. We also used this in the previous question, right? Yeah, let me just write. Yeah. Uh, so the next problem is, suppose the function f from 0, comma 1 to the n to 0, comma 1 is monotone, then which of the following statements about f is or are necessarily true? Select all the correct answers. The options are, if fx is less than equals to f of y, then x is less than equals to y. If x is less than equals to y, then f of x is less than equals to f of y. F can be computed by a circuit using just and OR gates, so we do not need NOT gates. And the complement of F is also monotone. So which of these are correct? Yeah, B and C are correct. So B is just a definition of monotone functions. Why is C correct? Like, do you have any idea? I'll prove that C is correct, but like, do you have any idea why C is correct?
Uh, yes, actually, both the gates are like if I have and as a result for some inputs. Now,
So your voice is breaking.
okay, just a minute.
Yeah,
So, am I clear now?
yeah.
Okay, so these functions are like monotone. What I mean by that is once I get like and as a result 0, so even if I like change some bits to 1, the result will be 0. Like
Okay, if you just
and
change one bit to
similarly,
one, right?
yeah, and similarly for OR, if once I have the result as 1, changing any bit like bits to 0 would also still give me 1.
Right, but so that tells us that and OR gates are monotone. But why does that imply that every monotone function can be computed just using and OR gates?
Because like every like function can be represented using and or and not, and like not, but what I intuitively believe is not is the one which breaks the complement of monotonicity. uh,
Yeah, you are right. Not is basically what breaks monotonicity. Yeah, but this is not a formal argument for this, right?
yes, yes.
So we'll see that. Yeah, it's it's mostly along these lines that once you change a bit to one, yeah, it's mostly along those lines.
It's intuitive, but like I don't know whether
Yeah,
how to prove it formally or not.
yeah. Okay, so okay, let me first show that. Okay, so first let me. So this, since multiple options can be correct, we first need to show that. We also need to show that A and D are not correct. So yeah, let me first show that B is correct because definition of monotone function. A is not correct. Yes, so to prove that A is not correct, all I need to do is to come up with an F which satisfies this but is not monotone, right? So let F from 0, comma 1 to 0, comma 1 and F of x is equal to 0 for all x. Then so this function is monotone, and now we need to check if uh, this is true or not, right? So, okay, f is monotone. Mm, f of 1, uh, f of 1 is less than equals to f of 0, and 0 is, well, let me write this. 1 is not less than equals to 0. So, we have an example of a monotone function for which this is not true. So, yeah, so where here x is 1, y is 0, and so can't be true in general. What about D? So for D, what we can do is we can create a monotone function for which its complement is not monotone. And yeah, it's also a function from 0, comma 1 to 0, comma 1. F of x equals x for all x. Uh, F is monotone. Uh, okay, F is monotone. Now what is F complement? F complement is so F complement of x is equal to the uh, is equal to the complement of f of x is just x complement, right? So 1 is equal to f complement 0. Why? Because f of 0 is 0. This is sorry. Okay, I should have written like this. So 0 is equal to f complement 1 is less than or equals to uh, f complement 0, which is equals to 1, right? But 0 is 1 is not less than 0. So F complement is not monotone. Yeah, so we have an example of a monotone F for which its complement is not monotone. So D is false. Now let's prove why C is correct. So this is going to be slightly longer. Okay, so construct a circuit. So what I'll do is I'll first construct a circuit using just AND and OR gates, and then prove that that circuit computes F. Okay, construct a circuit C as follows. Uh, for all x in 0, comma 1 to the n, such that f of x equals 1, let Sx be the set of all I such that xi is equal to 1. So what I'm doing is I'm looking at all the strings which evaluate to 1 under the function, and for all such strings, I'm picking up the coordinates of bits which are 1. So for example, if the string were 0, 1, 1, 0, 1, then 0, 1, 1, 0, 1, then SI would have been SI would have been 2, 3, and 5. Okay, yeah. So this is Sx, and C is R over all x in 0, comma 1 to the n, such that f of x equals 1, and over all I in Sx xi. Yeah. So this is the circuit. Before I prove that this circuit computes f, is the definition of the circuit clear? In the meantime, let me write down the claim. And a page this one. Yeah, so I hope the definition of the circuit is clear. So then let's write. So we have to show two things, right? For every x in 0, comma 1 to the n, there are two cases, either fx equals 0 or fx not equal, fx equals 1, right? In both the cases, we are supposed to show that cx equals 0 and cx equals 1, right? So that's exactly what we'll do. For any n, exactly one of the following is true. Case 1, fx equals 1. So in this case, uh, the gate evaluate to, so cx equals 1. Yeah, so okay, so my claim is that in this case, this gate would evaluate to 1. First of all, notice that this gate is present in the circuit because it's OR over all x for which fx equals 1. So this gate is present over here. Now, what is Sx? Sx is the set of all I at which for which xi equals 1, right? So this is just an end of ones, so it will be true. And since it is true, and the topmost gate is an OR gate, it doesn't matter what other gates evaluate to, the output of CS would still be 1, right? Is this fine? Yeah. And this is where we are sort of using what you suggested, that and OR are monotone. Yeah. So this part of the argument used it. And even the next part will use it. The second case is slightly trickier. Second case is f of x equals 0. So what do I need to show? I need to show that in this case, all of these gates would evaluate to 0, right? So we need to show that for all y in 0, comma 1 to the n, such that f of y is equal to 0, uh, the gate and I in Sx, sorry, and I in Sy, xi equals to 0. Okay, so what does the circuit have? The circuit have all gates. Uh, okay, the circuit has an AND gate for every y for which fy equals 1, right? And what does the gate look like? That gate looks like AND I in Sy, yi, right? However, now what do I want to show? I want to show that in this gate, when I plug in x, I get 0, right? And if I plug in x in this gate, what would happen? Y I would be replaced by xi, right? So that is why I need to show that this is 0. Is this fine? Yeah. Okay, so then how do we show this? So suppose not. So suppose and there exists a y in 0, comma 1 to the n such that, wait, this should be 1, that f of y equals to 1 and this is equal to 1. Okay, but in that case, mm, for all j in n, yj equals 1 implies xj equals 1. So let's understand this. So we are saying that for every y, so that f, there exists a y, so that fy equals 1 and this gate evaluates to 1. Okay. Now the claim is that this would imply the thing written over here. Why? Because what is Sy? Sy is the set of all indices where uh, yj equals 1, right? And this gate evaluates to 1. What does that mean? That means that whenever yj equals to 1, xj has to be 1, right? So is this fine? Is this claim clear? Yeah, because this is the crucial part of the argument. So, okay, now we have this. This means that y is less than equals to x. So this is how it's defined, right? Y is less than equals to x if whenever yj is 1, xj is 1. So, yeah, but since f is monotone, this means that uh, f of x equals 1. Why? Because f of y equals 1, right? Which contradicts the assumption that f of x equals 0. So no such y can exist. And uh, the, yeah, so since no such y can exist, all of these are 0. So that or is also going to be 0. And hence, yeah, so Cx is also 0. So in the first case, Cx and Fx for both 1. In the second case, Cx and Fx for both G are both 0. So C exactly computes it. Is this fine? And yeah, so we have taken care of all four options. Yeah. Okay, yeah. So then
Uh,
let's,
just
yeah.
to make sure, like case one doesn't use the fact that f is monotone, right?
No, no, so in case one, what our goal is the following. It's to construct a monotone function for which this statement is not true.
No, no. For the proof, like in
Oh,
the proof.
okay. In this case,
Yes, yes. The part one, the case one. Like I don't think it uses the fact that f is monotone.
no, 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 no. Yeah, that does not use the fact that f is monotone.
Okay.
It's
But
only case
looking
two.
at the case two, we need that f is monotone.
Yes.
Okay. So, like, how would we formally prove that using NOT gates would break monotonicity?
Okay, so first of all, uh, every monotone function can be computed by a circuit containing NOT gates as well.
Yes, yes,
In particular, just that DNF or CNF that we saw last time, right?
sure.
So just because a circuit has NOT gates does not mean that it does not compute a non-monotone function. But what we can show is that there are circuits which contain NOT gates and do not compute monotone functions. In particular, we saw it over here, right? Option B. So over there, the circuit was just this, right?
Yes, yes.
Yeah. Okay, so then let's look at the next problem. The next problem is consider the following function disjoint. Disjoint of x1, x2 to xn, comma y1, y2 to yn, outputs 1 if and only if this sum I in 1 to n xi yi equals to 0, then xi yi in 0 are in 0, comma 1. Then the question is this joint is in NC0, AC0 but not in NC0, NC1 but not in AC0, and AC1 but not in NC1. So which of these is correct? Okay, so it's in AC0 but not in NC0. Let's see why. So first I'll show that it is in AC0 and then I'll show that it's not in NC0. Yeah, so all we need to do to show that disjoint is in AC0 is to come up with a circuit with constant depth, polynomial size, and it can contain and or case of unbounded fanning, right? So sum over I in 1 to n xi yi is equal to 0 if and only if for all I in n xi yi equals 0, right? Why? Because xi yi lie in 0, comma 1. So in particular, none of them are negative. So there is never going to be any cancellation at all, right? So the only way the sum can be 0 is that if each and every one of them is 0. And so this suggests a natural circuit, right? So uh, for disjoint xn y1 yn is just or I in 1 to n xi y. Is this claim fine? Because if any one of this is 1, the sum won't be 0. Oh wait, no, okay. I need a not over here. Yeah, sorry. Okay, so uh, when is something not in disjoint? It's not in disjoint if this. Okay, so when is something in disjoint? It's in disjoint if this sum is 0, right? And that's this sum is 0 if and only if all of these are zero. So if and only if this is zero, right? So I should put a not over here. Why? Uh, because whenever all of these are zero, then disjoint is zero, and so my circuit should output two. Sorry, this sum is zero, and so my circuit should output one, right? Because this string isn't disjoint. So there was some confusion over here, but I hope this is fine now. Yeah, and this naturally gives us a circuit, right? Oh, by the way, yeah, I need to write one more thing. Also, xi yi is the same as xi and yi, right? Why? Because when I is xi yi one, if and only if both xi and yi are one, and in and if xi and when is xi and yi one, when both of them are individually one, right? These two are exactly the same thing. So this suggests the following circuit: NOT gate, OR gate, AND gate, x1, y1, similarly to x and yn. Yeah, what's the size of this circuit? N plus 2. So we have N gates over here, one over here and one over here. So that's N plus 2, and depth is 1, 2. Yeah, so this joint is in. Is this fine? Okay. So for NC0, so what I'm going to claim is the following. A function in NC0 can only depend on constantly many variables. So is this claim, okay, let me write it first, then I can ask you. Yeah, so this is the claim. So is this claim clear, or should I tell you why this is the case?
Please tell why is this the case?
Okay, yeah. So okay, so what does an NC0 circuit look like? An NC0 circuit has only spanning two gates and or only gates of spanning at most two because not gate has spanning one, and it has constant depth, right? So how many inputs can this circuit take? So it's a directed acyclic graph with constant depth, and every gate can have at most two uh, two inputs, right? So how many uh, how many inputs can this circuit take? Yeah, okay, maybe two to the depth plus one. Yeah, it's roughly two to the order depth. But yeah, maybe there is a plus one, minus one over there. So yeah, yeah. So yeah, so the reason is exactly this. A circuit with a depth delta can take about 2 to the order delta inputs. And since for an NC0 circuit, uh, the depth is constant, that means it can only take about 2 to the constant, that is again constant input, right? So any function in NC0 can depend on only constantly many variables. Is this fine now? Okay, yeah. So if this is fine, then to show that disjoint is not in NC0, all I need to do is to show that it depends on more than constantly many variables, right? In particular, what I'll do is I'll show that it depends on all the variables. Okay. So disjoint, why? Because disjoint, okay. So okay, okay, let me write it like this. Disjoint depends on, that's fine. Okay, so let A be a string which is zero everywhere. But yeah, let A and B both be such strings. So let A comma B be 0 to the n. Uh, A prime be, how do I write it? Okay, A prime n and A prime be the string that is 0 everywhere except at its ith bit. Okay, a better way to write it is this string such that AJ, that is the jth bit is 0 if J not equals I and AI is 1. Now, uh, disjoint A comma B is equal to 0. Why? Because A and B are both, yeah, so A and B are both uh, all zero strings. And I want to say that disjoint, oh, I can't define B prime like this. The proof is in this. Similarly, P prime is a string such that Pj is equal to 0 if I not equals to j, and mm, Pi is 1. So now, okay, so sorry for the confusion. So now there are four strings A and B and A prime B prime. A and B are equal and all zeros, and A prime B prime are also equal. They are all zeros except for the ith bit, at which both of them are 1. So now disjoint AB is 0, but disjoint A prime B prime is not equals to 0, right? What does this mean? This means that any circuit computing must take uh, xi, yi as inputs. Okay, yeah. So we have four strings AB and A prime B prime. I should write primes everywhere. Yeah. Yeah, so we have these four strings, and disjoint of AB is zero, but disjoint of A prime B prime is not zero because AI BI is one, right? And now suppose that we have a circuit computing disjoint which does not take AI and BI as inputs, right? Then it would completely miss that disjoint A prime B prime is non-zero, right? So is this clear?
Please repeat it, your
Yeah, okay.
voice.
Okay, so we saw that disjoint AB is zero, but disjoint A prime B prime is non-zero. So now suppose we had a circuit C which did not take Xi and Yi as inputs, right? Then as far as the circuit is concerned, AB and A prime B prime are exactly the same strings because the only place at which they differ, in particular the ith bits, Xi and Yi, the circuit is not looking at that bits at all, right? So if for the circuit AB and A prime B prime are the same, its output must be the same, right? So that circuit cannot output 0 for AB and 1 for A prime B prime. And yeah, so that circuit must either say that disjoint AB is 1 or that disjoint A prime B prime is 0, right? Because its input is output on both of these should be exactly the same. So every circuit computing disjoint must take xi via as inputs, and this argument works for all xi for all I in n, right? Is this fine or should I repeat this again? Yeah. So in particular, any circuit computing disjoint must take at least like all of these as inputs, right? But in that case, it cannot have constant depth if we restrict all the gates to have fan in two, right? So no constant depth circuit whose gates have just fan in two can compute disjoint, and so disjoint is not in NC0. Yeah, and this shows that the correct option is AC0 but not in NC0. Is this fine? Then let's look at the next problem. Yes, the next problem is which of the following is or are known to be true? Select all the correct answers. For all I, PCI is in P slash poly. NP is not in P slash poly. Uh, P is not in NP is not equal to P slash poly. P is strictly contained in P slash poly, and P slash poly is contained in NP. So which of these are correct? Or should I should connect the charge for my laptop? Yeah. Okay. Yeah. So B and C are correct. Okay. Why is D not correct? Yeah. So in particular, Kara-Clifton theorem shows that if P in P slash poly in NP, then pH collapses to the second level. But the question of whether pH collapses to the second level or not is an open problem. So we can't see anything about option B. But why is option A not true? Okay, actually option A is also true. And so let's see why A, B, and C are true. So let's start with B first. We'll look at A at the very end. So why is NP not equals to P slash poly? That is because P slash poly contains uh, some undecidable languages. For example, the U-halt language, which is just a unary version of the halting problem. Since NP only contains decidable languages, NP can't be equals to P slash poly. Similarly, for option C, P is definitely contained in P slash poly, but P also only contains decidable languages. So P is strictly contained in P slash poly. And now let's see why A is correct. Okay, so the only problem with A being correct is the following. What does an ACI circuit look like? It it is made up of AND, OR, and NOT gates, and it has polynomial size. So far, it is fine. However, the gates in it can have unbounded fan-in, and on the other hand, in P slash poly, a language is in P slash poly. Oh, okay. So, what was the last thing that you heard? Okay. So, can you hear me now, or is it still stuck? Okay. Yeah. Yeah. So, we want to prove that option A is correct. So now, when is a language in ACI? It is in ACI if it is decided by a circuit family, which is made up of AND, OR, and NOT gates, is of polynomial size, and has depth order log I, right? So, what is the problem with an ACI circuit being in P slash poly? Well, in an ACI circuit, the gates can have unbounded fan-in. On the other hand, in a P slash poly circuit, they require it to be of polynomial size and gates to have fan-in too, right? So, in particular, in the ACI circuit, has polynomial size, but its gates can have unbounded fan-in, right? And that unbounded fan-in is what is apparently preventing ACI from being in P slash poly. Okay, so if this issue is clear, let's see how to solve it. So we know
Uh,
that for, yeah,
so where does the fact come from that P slash poly needs the gates to have a bounded fanning?
okay, so how do you define P slash poly? What was the exact definition of P slash poly? It
Uh,
was
l-
that,
like a
yeah,
polynomial size circuit family.
right. So generally, when we say that as a, so generally when we consider a Boolean circuit, we consider Boolean circuits with like fan-in too, right?
Yes.
Yeah, so it's sort of implicit in the definition of P slash pool.
Okay, it's implicit, right?
Yeah, but you are right. Spanning doesn't matter a lot. So in particular, what we know is this. For all I, yeah, so for we know this that for all I, ACI is an NCI plus one, right? And what does an NCI plus one circuit look like? It is made up of AND or NOT gates of pan in 2, has polynomial size and depth order log n to the I, right? So now the circuit is just made up of AND or NOT gates of pan in 2, right? So this is in P slash poly. Is this fine? Yeah. So all three, A, B, and C are correct.
Just one thing with the
Yeah.
option B. What does it actually mean when we say that a language is undecidable? Uh, like P slash poly contains some undecidable languages. Like, does
Okay.
there exist a circuit for it? And if so, shouldn't the circuit decide the language itself?
Okay. So here's a okay. So let's say you have a circuit for the halting problem. Okay. What does that mean? Yeah. First of all, you don't have a circuit for the halting problem. You have a circuit family for the halting problem, right? So you have a circuit family Cn such that the nth circuit decides halt for all strings of length n. Okay. That is how you define a language recognized by a circuit family, right? Now the problem is the following. Just because there exists a circuit family does not mean that you can compute that circuit family using a Turing machine, right? Now, suppose there exists a circuit family for U-halt, but you cannot compute that circuit family using a Turing machine. In that case, you do not have any Turing machine that decides U-halt, right?
Like, but why are we using Turing machines here? Like, uh,
Okay, so what's the definition of a decidable language?
a language for which a Turing machine stops in a finite amount of time.
Right, so a language is decidable if there exists a Turing machine deciding it, right?
Yes.
So if you want to say that U-halt is decidable, we will have to somehow come up with a Turing machine deciding it, right?
Okay, so what does exactly mean that P slash poly contains some language, not decidable or indecidable? If I
Okay,
simply
so
say that P slash poly contains some language, so it means there exists a circuit for it,
a circuit family. Okay, so let me
a
write down
circuit
the
family.
exact.
Yes, yes.
Right,
Okay.
yeah. So L is in P slash poly if there exists a circuit family Cn n greater than equals to 1 such that size of Cn is equal to poly n for all n and for all x in 0, comma 1 to the n, x is in L if and only if Cnx. Yeah, so this is what it means to say that a language is in P slash poly.
Right.
So now,
So
yeah,
if I say that U halt is in P slash poly,
right,
so that means for a particular length string,
right,
like for a particular n, this implication works. Like if x belongs to L,
yes,
like it should give me one, and if x
right,
naught belongs to L, it should give me zero. So
yes.
that is like exactly what we are trying to solve, right?
Your voice broke. So the last thing I heard is like that is exactly.
So that is exactly what we are trying to solve, right? Like whether you
No,
hold.
no, 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 no. So that's not what we are trying to solve, right? We are trying to find a Turing machine that does that. Because what's the definition of a decidable language? A language is decidable if a Turing machine can decide between whether a string is in the language or whether a string is not in the language, right? Hello? Yeah, can you hear me? Because I can't hear you if I speak it. Yeah. Can you hear me now?
I don't think you can hear me.
Oh, yeah, okay, I can hear you now.
Okay, okay. So
Yeah,
what I was trying to say that right, you said that we are trying to find a Turing machine which can tell me whether we halt or not,
right.
right? So
So what's the definition of a decidable language?
like a language is decidable if there exists a Turing machine which infinite number of steps can accept or reject, like can read.
Right.
Yes.
Yeah. So that's the definition of a decidable language. And over here, what do we have? We have a circuit family which can decide language, right? So now from this circuit family, we should somehow to argue that UHALT is decidable. From this circuit family, we should be somehow able to construct a Turing machine that decides UHALT, right?
Okay.
But the, so what happens is that okay, so when can this happen? This can happen if there exists a Turing machine that when I give it n, it can output the description of Cn, right? So if I had a Turing
I
machine which on input n can output the description of Cn, all I have to do is take x, compute like output a description of Cn and evaluate x on Cn and see what its output is, right?
yes. Okay.
Yeah. So if you were to look at the circuit family for U-Halt, it's pretty clear that you cannot do this for any Turing machine. So in particular, there does not exist any Turing machine that can output that given n can output Cn.
Okay. So there doesn't exist a Turing machine which can like output the value of Cn.
Right.
Okay. So like doesn't the fact that Cn is one
Mhm.
tells me that okay, this is solvable, but I'm not able to find a Turing machine.
Right. Okay. In fact, that is true for any language, right? For any language, X is in L if and only if like something is one, right?
Yes. Yes. Yes.
Okay. So how do you okay? So you can define the function f as follows: fx equals one when L is in the language, fx equals zero when L is not in the language, right?
Yes.
And so X is in L if and only if fx equals one. But just because such an f exists does not mean you can compute it using a Turing machine, right?
Okay. Yes.
Yeah. And it's that which gives you undecidability or semi-decidability in case of you want.
Okay. Okay. I got it now.
Yeah. Yeah, so circuits are sort of weird in that they can efficiently decide undecidable languages. Yeah. So yeah, if that's fine, we can move on to the next problem. Yeah, so the next problem is uh, consider the language odd that contains an end-bit string x equals to x1 to xn that are binary representations of odd numbers. What is the smallest value of I such that odd is an NCI? Enter the answer in numeric form. So, what's the smallest value of such an I? So, in particular, what is the smallest size of any circuit family deciding odd? Okay, yeah. So why is that?
Well, I just need to check the last bit, right?
Yeah, so all you need is this. This is the circuit. Okay, so let me write it. So, X is odd if and only if Xn is 1, right? And so this is the circuit. You have inputs x1, x2, xn, and all you are doing is just forwarding this as output. So there is no gate in the circuit. And so obviously it's that's 0 and yeah, you see 0. Is this fine? Okay, so the next problem is yeah. Let L be a language which can be computed by a P-uniform circuit family, then L is also in P. True or false? Okay, so first of all, what does it mean for a circuit family to be P-uniform? Okay, so it's true, and here's the reason why. So a circuit family said to be, okay, circuit family Cn to be P-uniform if there exists a deterministic Turing machine M, uh, polytime. A polytime deterministic Turing machine M such which on in such that for all n in n on input 1 to the n, M outputs the description of a Cn. So basically, a circuit family is said to be P-uniform if we can generate every member of it in polynomial time. And the claim is that if L is decidable, if L can be computed by a P-uniform circuit family, then it's in P. And the reason is fairly simple. So suppose L is computed by a P-uniform circuit family Cn, then consider a deterministic Turing machine M prime, which on input X simulates M on input 1 to the size of X to obtain C size of X and then evaluates a C size of X, evaluates and outputs. Yeah, so this is what the Turing machine M prime does. And is the definition of M prime clear? Yeah. So now M prime clearly decides L. Why? Because suppose X were in the language, then Cx of X would be 1 and M prime would output that. If X were not in the language, then C size of X would be 0 and M prime would output that. So the output of M prime is 1 if and only if X is in the language. So M prime clearly decides L, To show that L is in P, all we need to do now is to show that M prime runs in polynomial time, right? So since uh, L is in P slash poly, sorry, yeah, okay, so since Cn is circuit family, size of Cn is equal to poly n. So this is my claim that the size of Cn equals to poly n. So why is this claim true? Okay, so what do we know about Cn? We know that there exists a polynomial time Turing machine M, which on input 1 to the n outputs the description of Cn, right? Oh, sorry, I should write Cn over here like this. Yeah, and since a now if okay, since M outputs Cn, if the running time of n is poly n, it can only output poly n many bits, right? So the size of Cn, so the size of a description of Cn is poly n bits, and so the size of Cn itself is poly n bits. Sorry, it's poly n. So the size of Cn is poly n, and because of this, so we can evaluate C size of x on x in poly size of x time, since M also terminates. So M is the Turing machine that outputs the description of C size of x. Time, the running time of M prime, which is the sum of these two. Running time is poly size, poly n. Yeah, is this fine? Yeah. So if this is fine, let's look at the next problem. So the next problem is the following. Consider the function XOR, which takes as input two bits x and y and outputs 1 if and only if x is not equals to y. What is the minimum number of gates required to compute the function using just AND, OR, and NOT gates? So, would you like to take a guess what the minimum value is? I can throw a, okay, how can you compute this using three gates? So, do you have a circuit in mind which can do this using three gates? Yeah, so this is the truth table of this 0, 1, 1, 0. Okay, yeah. So 5 gates is true. You can compute this using 5 gates, but is the minimum possible? That's the question. So let me first show you a circuit using 5 gates. And okay, let me just tell you the answer is 4. So what I'll do is I'll first show you a circuit using 5 gates. Then I'll show you a circuit using four gates, and I'll very at a very high level tell you how you can prove that no circuit of three gates computes it. So to prove that no circuit of three gates computes XOR, that proof is very long. So I won't like give you that proof, but I'll tell you how the proof proceeds. So this is the truth table for XOR, and so XOR of XOR Y is just uh, not X and Y. So not X and Y corresponds to this, or X and not Y, right? So we have this formula for XOR. This naturally suggests a circuit, right? Put an OR gate at the top, have two AND gates, X, Y, X. So the size of this is 5 gates. Okay, so when we use this description of XOR, we got a circuit with 5 gates. However, notice that this is an OR of ends, right? There is an so instead of looking at an OR of ends, we could have also looked at an AND of ORs, right? So that's so let's see what happens when we look at that description of XOR. Uh, X or Y and X complement or Y. So I'm claiming that this is XOR. Why? Okay, what happens when both X and Y are zero? When both X and Y are zero, this is zero. So this entire thing is zero. Similarly, when both X and Y are one, this is zero. And so the entire thing is again zero. When X is zero, Y is one. This is zero, this is one, so this is one, and this is one, this is zero, so this is also one. Similarly, when X is one, Y is zero, this is one, this is zero, this is zero, this is one, so both are one. So this is the same as XOR. And now let's see what happens when we use this description to compute a circuit. So this gives us the following circuit. And or or X, Y, not gate, not gate. So even this circuit has 5 gates. However, the benefit of this circuit over this circuit is that both of the NOT gates are under the same OR gate. So does this suggest something? So okay, the goal is okay. Let me tell you what we are going to do. We are ultimately going to replace these two NOT gates with just one NOT gate. Can you see how we can do this from this circuit? Yeah, it's using De Morgan's law. Okay, so what does this part of the circuit compute? It computes this, right? However, using De Morgan's laws, this is the same as X and Y. And so we can draw this circuit. Have just one NOT gate over here, have an AND gate as an input, and this has 4 gates. So is this circuit fine? Yeah, so if this circuit is fine, uh, all this circuit tells us is that the answer is at least four, right? Sorry, at most four. It can be three as well. However, it turns out that you cannot compute XOR using any circuit of three gates. And I won't prove it, but the proof is as follows. And at least you can prove it using this template. Template is, so there are only like constantly many circuits with three gates, right? And what you do is you go over all those circuits and argue that the output of that circuit is not the same as XOR. Okay, yeah. So this is a very high level overview of why how you can prove that three gates cannot compute XOR. I won't like do this because this is a case analysis. I think there are like four or five cases. Sorry, three or four cases. Is this fine? Yeah, so this is fine. Let's move on to this year's week 7 practice assignment. Yeah. So the first problem is, suppose Fn equals to 10 times 2 to the n and Gn equals to 300 times n times 2 to the n, then is it true that size of Fn is strictly contained in size of Gn? True or false? Okay, so it's false because well, Tupanov's theorem tells us that any function can be computed by a circuit of size order 2 to the n over n, right? So, since, okay, so let me write it like this. So, this class size 2 to the n over n contains all languages and hence, okay, since size 2 to the n over n is contained in both size size of Fn and size of Gn. Both size of Fn and size of Gn contain all languages, so they are exactly the same. The set of all languages. Yeah. Yeah, so both size of Fn and size of Gn contain all languages, and so they are equal, and so this statement can't be true. Is this fine? Yes, so I hope this is fine. Then we can look at the next problem. Yeah, so the next problem is, which of the following statements is or are currently known to be true, so that all that apply. All the languages in P slash poly have efficient algorithms. P slash poly contains undecidable languages. There are languages in P slash poly that require exponential size circuit families in order to decide. And P slash poly contains all the unary languages. So which of these are correct? Okay, so let's go over all the options. So the first option is all languages in P slash poly have efficient algorithms. Well, this can't be true because we know that P slash poly contains undecidable languages. And forget about an efficient algorithm. An undecidable language does not have any algorithm, right? So A is not true. What about B? B is P slash poly contains undecidable languages. That is true. So yeah. What about C? There are languages in P slash poly that require exponential size circuit families in order to decide. This is false because what is the definition of P slash poly? It is the class of all languages which can be decided by polynomial size circuit families. So if a language requires exponential size circuit families, it won't even be in P slash poly. So C is false. And option D is P slash poly contains all unary languages. This is also true. So did you see this in class that P slash poly contains all unary languages? Or should I prove it?
Can you
Right.
prove that?
Okay, yeah. Okay. Okay, so a unary language only contains strings of the form 1 to the n for sub n. Okay, so this is the definition of unary language. And now what we want to do is we want to construct a circuit family that decides this language. Now observe that there for any n there is exactly one string which okay there is at most one string of length n which can be in uh, okay let me call this language something. Yes, so for any n there can be at most one string of length n which is contained in u, and that string is 1 to the n, right? So here's how we can consider a circuit family to decide un. So define Cn as follows. So Cn is 0 if 1 to the n is not in U, and Cn is this circuit. Why do this? Yeah. So my claim is this circuit decides the language U. Why? So pick a 1 to the n. So okay, first of all, pick any string. If it is not of the form 1 to the n, then it's not going to be in the language, right? So let's just focus on strings of length 1 to the n. So if for a particular n, 1 to the n is not in U, then Cn output 0 because it is 0. And if for a particular 1 to the n, 1 to the n is in U, then since all of these are 1, the output is 1 and C outputs 1, right? So for all strings of the form 1 to the n, C decides them correctly. What about a string that is not of the form 1 to the n? Well, it's so Cn is either 0 or it's this, right? So if any one of these is not equals to 1, then the output is still 0. So for all strings not of the form 1 to the n, Cn is always going to output 0. And for all strings of length 1 to the n, Cn outputs 0 if it's in 1 to the n, if it's not in 1 to the n, and 1 if it's in 1 to the n. So Cn correctly decides the language U. Is this fine? So basically the fact that we used was that there is at most one string of size n which can be in U, and we hard coded the string in the circuit. Yeah. And in fact, you can use this to prove that uh, P slash poly contains undecidable languages because you just take an undecidable language and convert it into unary. Yeah. Okay, so now let's look at the next problem. The next problem is which of the following facts uh, is crucially used in the proof of the Karp-Lipton theorem? The options are set is differentiable, set is integrable, set is reflexive, set is antisymmetric, and set is self-reducible. So which of these is true? So this is just a recall question, and the answer is set is self-reducible. So this so this was crucially used in the proof of Karp-Lipton theorem, and if you don't use this, you still get something like Karp-Lipton theorem. But so Karp-Lipton theorem implies this, right? NP in P slash poly implies pH equals to sigma 2. So if you don't use set is self-reducible, then you get something like pH is equals to sigma 3. Sorry, pH is contained in sigma 3. Yeah. Yeah, but the proof of the Karp-Lipton theorem that we saw in class crucially used this. So I hope this is fine. So then let's look at the next problem. So the next problem is NAND is a Boolean function that returns 0 if and only if all input bits are 1. It is a negation of the AND gate. Suppose we define a new complexity class NAND NCI to be identical to the definition of NCI, except that instead of allowing OR, and NOT gates, we only allow NAND gates of Pandin 2. So, which of the following statements is the most accurate one? NAND NCI is in NCI, NCI is in NAND NCI, both are the same, and neither NAND NCI nor NCI is a subset of the other. So, which of these four are true? Okay, so A is certainly true, but okay, it turns out both A and B are true, and therefore C is true. Yeah. And so, yeah, in the question, we are supposed to pick the option that is the most accurate, and C is the most accurate because both are true. So, let me prove it now. So, yeah, first claim is what you said. NAND NCI. So, why is this claim true? Yes, no. Let L be in NAND NCI. Then there exists a circuit family Cn such that for Cn that decides L, And for all n, size of Cn is poly n, depth of Cn, order log n to the I, and Cn only contains NAND gates. Okay, so now, oh, I don't have enough space. Yeah. Now we can replace each NAND gate with a NOT gate and an AND gate, right? Why? Because NAND is a negation. Because NAND is the negation of NOT, and so the negation of NAND. Okay, so NAND is the negation of and so if I have a NAND gate that takes in inputs F and G, I can replace that by an AND gate that takes input F and G, and then feed the output of that AND gate into a NOT gate. That would compute the same function as the NAND gate. Is this fine? Yeah. So with a NOT gate and an AND gate. So what would be the size of this new circuit? New circuit. Yeah, so in this circuit, so in this change, I'm replacing one NAND gate with two gates. So the size of the new circuit is at most two times size of Cn, right? Which is equals to poly n squared. And what is the depth? So again, so I had a NAND gate. I'm replacing it with an AND gate and a NOT gate. So the depth can also increase by a factor of at most two, right? And this is still order log n to the I. So now I have a circuit family with of poly n size and uh, order log n to the I depth containing just AND and NOT gates. And so L is in NCI. So this was one direction of the proof. Is this fine? Okay, let me try to move this. See if I have enough space. Then yeah. Okay, I don't think I'll still have enough space. Let me do this. Claim three. Okay, so this claim shows that this is true. Now we want to show that this is true, to prove that this is true. So the claim is yeah. Okay, so what do we have? We have the, let's pick an L in NCI. Then, yeah, it's almost this. Then there exists, yeah, so if, oh, what's that? Yeah, so if L is an NCI, we have a circuit family Cn that decides L, and for all n, size of Cn is poly n, depth of Cn is order log to the n I, and Cn contains and, or, and non gates. So now what we're going to do is we are going to replace all the AND or and NOT gates in Cn by NAND gates. And let's see how we can do that. So we can replace all gates by NAND gates as follows. Case 1. So let's see how to replace a NOT gate first. Okay, so NOT X, the claim is this, NOT X is the same as NAND X comma X. Okay, let's see why. So suppose X were 0, then NOT X is going to be 1. Okay, now X is 0, so this is 0, this is 0, and of this is 0. And so the NAND, which is a negation of AND, is 1. So when X is 0, NOT X and NAND XX are both 1. Similarly, when NAND is 1, so sorry, when X is 1, this is 0, this is 1, this is 1, so the AND is 1, and therefore the NAND is 0. So NAND X comma X is equal to NOT X. So we can replace a NOT gate by a NAND gate like this. So NOT gate would have just one input. We are just going to feed that input twice to the NAND gate. Case 2, AND gate. Okay, so X and Y is negation of X and Y. And what is the negation of X and Y? It's just non-AND, right? So this is NAND. Okay, let me write it below. And okay, so what is not of NAND? Okay, so now we can just replace this not by this construction. So this is NAND of NAND X comma Y, NAND X comma. So is this transformation fine? Okay, so then let's look at the third case, or. Yeah, so by using De Morgan's law, we can write this as not of not X and not y, right? Now, not of and is just NAND. This is NAND dot x comma not y. So now we have two NOT gates and we can replace them by NAND gates using this construction. Yeah. So let's see how to do that. So this is NAND of NAND x comma y comma sorry x comma x comma NAND of y comma y. So so this is fine. Then so then what we are going to do is in CN we are going to replace NAND and OR gates in this way. This would give us a circuit computing the same function or rather the same language, uh, but using just NAND gates. To show that this is a NAND NCI, we need to do two things. Show that the size of the circuit is still poly n and the depth is still order log to n to the I. But those are simple. So let's look at those. So what's the size of the new circuit? So the size of the new circuit. Okay, so what am I doing? Every NOT gate is replaced by just one NAND gate, is replaced by three NAND gates, and every OR gate is replaced by three NAND gates. Okay, so the size of the circuit, new circuit, is at most three times the size of CN, right? Which is still poly N. Similarly, okay, so what will happen to the depth? So for how am I replacing an AND gate? So I'm replacing an AND gate like this. So okay, so uh, first of all, this replacement does not in the replacement of for NOT gates does not increase the depth because I'm replacing one NOT gate with a NAND gate. However, over here, so this blows up the depth by a factor of two. Similarly, in the case of uh, OR, I'm also replacing uh, an OR gate with a similar construction, right? It's again NAND of two NANDs. So both of these have the same sort of replacement. So the depth increases by a factor of at most two, and this is still order. Yeah, so the size is poly and the depth is order log n to the yeah. Yeah. So is this fine? Yeah. So we have shown that NAND NCI is an NCI as well as NCI is in NAND NCI. So both are equal and option C is correct. Okay, so now let's look. Okay, so that was all for week seven's content. So now we have some minutes, like we have 13 or so minutes. So let's look at some problems from this year's week six assignment. So if you have some problems that you would want me to explain from this assignment, you can tell me, or I can like go over them in sequence. So do you have some preferences about problems which I should solve first? Okay, yeah. Then let's just look at these in sequence. So the first problem is which of the following are a complexity measure for the circuit model of computation? Mark all the correct options. The options are size, depth, time, and number of wires. So which of these are correct? Yeah, so it's size, depth, time is not there, but number of wires is also complexity measure for the, yeah, it's ACD. Wait, ABD, right? Time is not there. I hope it's fine. Yeah, yeah, it's ABD. So everything except time works. Now let's look at the next problem. So next problem is which of the following are known to be correct? Mark all the correct choices. BPP is in PP, NP is in PP, BPP is in sigma 2, and BPP is in NP. So which of these are correct? Yeah, it's A, B, and C. Sorry, A. Yeah. This was just a recall question again. There was nothing to throw over here. Okay, so now let's look at the third problem. We need to build a circuit that takes as input an n-bit integer x equals to x1 to xn and outputs 1 if and only if x is divisible by 16. Which of the following gives the tightest bound on the size of such a circuit? The options are order n, order log n, order 1, and order log n. So which of these is the tightest bound? Yeah, it's order 1. Why?
We just need to ensure that last four bits are 0.
Yeah. So x is divisible by 16. By 16 if and only if there exists an integer. Okay, n is the number of bits. Let me write n such that x equals to 16 times m. So the binary of x would be equals to binary of 16 times the binary of m. So x1 to xn is equal to 10000. This is the binary of 16 times the binary of m. So x is divisible by 16. If and only if xn minus 3, xn minus 2, xn minus 1, and xn, all of these are 0. And here's a circuit to check this. So you have an AND gate at the top, four NOT gates. These these take as input is 3, xn minus 2, xn minus 1, and xn. And you completely ignore everything else. Yeah, so the size is just 5, which is order 1. So yeah, option C is correct. Is this fine? Okay. Yeah, you can also reduce this to 2 by just yeah, by using De Morgan's law. So we take an OR and then yeah, okay, take an OR of all these and then AND it. That would also work. Okay, so now let's look at this problem. Okay. Right. Yeah, okay, I think we can solve it in 7 minutes. Yeah. The problem is we are given this truth table and we are supposed to like find all the representations, all the Boolean formulas that represent this truth table. So yeah, this needs to be worked out. So let's work this out. Okay, so this is one and this corresponds to x complement y z complement. So I'm just writing this in the uh, DNF form. So x complement and x, x complement. Okay, this is one. So x complement and y complement and z. Or this is one. So this is x complement y and z complement. Or this is one. So x y complement z. Or this is one. So x y z complement. So now what we can do is observe that over here and here y complement and z are y complement and z are the same. So from these two we can do this. So we can take y complement and z common. So you get x complement uh, or x complement because there is an or between the two and y complement and z, sorry, and z, not z complement. So this is what we get from this two. And similarly from this two, there is yz complement, yz complement are the same. So you get or y and z complement and okay, let me put these in brackets. X complement or x. Yeah, so now x complement or x in both cases is 1. So this is just y complement and z or y and z complement. So is this an option y complement and z or y and z complement? Yeah. So this is true. And okay, so now let's see if D is true. Okay, first of all, A and B are not true because they have just two terms over here, and here we have four terms. And so I can further like simplify this by just distributing this all over and so I get y complement or y and y complement or z complement and z or y and z complement, sorry, z or z complement. So I'm just distributing this or over these ants and both of these are 1. So we are just left with, yeah, and this is exactly option. So C and D are correct and A and B are not. Is this fine? Yeah. Then let's look at the next problem. Okay. You can't even see the circuit in one screen. Okay, so okay, let me first read the problem. So we are given a circuit and we are supposed to find the output of the circuit is a certain number. The description is consider the following circuit. Here this parity gate This is a parity gate, and the parity gate outputs 1 if and only if the number of ones in the input is odd. And what's the question? The question is if x1 is 1, so if x1 is 1, x2 is 0, x3 is 1, and x4 is 0, what is the output of the circuit? So yeah, this also needs to be worked out. So let's work this out. So x1 is 1, so this wire is 1, so this wire is 0, x2 is 0, so this is 0, this is 0, so this is 0 or gate, this is 0, so this is 1, x3 is 1, so this is 1, this is 1, and x3 is 1, x4 is 0, so this is 0. So now at the top we have this parity gate. It has three inputs out of which only one is 1. So an odd number of
Last one is an OR gate. Last one is an OR gate.
oh wait, yeah, that's sorry. Yeah, so this is 1. Yeah, so we have a parity gate at the top, and two of its inputs are 1, which is an even number of inputs, so the parity gate is 0. Yeah, so the answer is 0. Yeah, so I think we are out of time, so let's stop for today unless you have any questions.
Just like if I can uh, ask that question again, I just went through the definition for p-poly. If I can take 2 minutes,
Okay, yeah,
right? So p-poly is the class of languages which are decided by polynomial size circuits.
yes,
So this is a class which decides some languages with using some circuits,
yes,
and this has some undecidable languages.
right.
So how does that work out?
Okay, so
Like the statement itself is kind of it is deciding and it has undecidable things.
okay, okay, but okay, so when we say that a language, okay, first of all, instead of using decidable languages, let's use recursive languages. Okay, so when is a language recursive?
Uh, like
A
when
Turing
we
machine decides it, right?
right,
And what does a language being in P/poly tell us? A circuit family decides it, right?
right.
But a circuit family does not necessarily imply a Turing machine, right?
But the essence of using a circuit family is only to cater to all different size inputs, no?
Right. Okay, so if you had a Turing machine and you converted that into a circuit family using Cook-Levin theorem, you would get a uniform circuit family, right?
Yes, yes.
But the circuit family that you get from P/poly need not be uniform, right? So for every n, you can do something very weird,
Okay, so the non-uniformity gives us the
right?
power that maybe some undecidable languages would also have a polynomial size circuits.
Right. In particular, she did something like this in the one question, right? Where is that unary thing question? Yes, over here. So over here, over here, what we did was for any unary language, we came up with a circuit family, right? And what did we do? We crucially used non-uniformity, right? Because for look at these two things. The circuit is like so we are hard coding the strings in the circuit, right?
Yes, yes.
This you need not be able to do using a Turing machine, right?
Yes, yes. Now I get it. Okay.
Yeah,
Thank you.
yeah. Okay, so if there are no more questions, we can end the meeting for today and meet next week. Thanks.
Okay. Goodbye.
Bye.
Thank you.